y'all, welcome back to another round of chemistry notes. This video is a very special video because it is the last set of notes in Unit 1. This video is going to talk about physical and chemical changes and properties, and by the end of it, you will know everything you need to know to do really well on your Unit 1 test. We are going to start by talking about physical properties. So a physical property is a characteristic that can be observed or measured without changing the identity of the substance, without changing what it's made of, what it is. So some examples of this would be color, right? I'm writing this video in a, maroon pen, and the fact that I've said this is a maroon pen hasn't suddenly turned that color into a different color. It's still maroon. Melting point is another example. Ice melts at 32 degrees Fahrenheit, or water freezes at 32 degrees Fahrenheit. We can measure this, we can test it, and the act of measuring it doesn't make that water into something else. Malleability and ductility, these tend to go together. Malleability is technically the ability to hammer something into thin sheets, but largely we use it to just mean moldability. Something like Play-Doh is very malleable because you can mold it, you can shape it with your hands. And ductility has to do with being able to draw things out into wires. If it is ductile, it can be drawn into wires. So we will talk about the properties of metals a little bit later in the year, and these words will come back up because malleability and ductility are both properties of metals. Another big one is density, which we've talked about several times so far this year. That is a physical property. You did a lab wherein you found the density of some BBs, and by finding their density, you didn't change the identity of the BBs, right? They were made of plastic, and you found their density, and at the end, they were still made of plastic. They hadn't burst into flames or done anything weird, unless you did the lab really wrong. Another example is solubility. This is the ability to dissolve. You can dissolve sugar into your tea, you can dissolve salt into water, you can dissolve chocolate powder into milk, and it doesn't change the identity of any of those things, it just mixes them together. Another good one is mass, right? You can throw something on a scale, you can weigh it, and it's still gonna have that same mass. You took the mass of your BBs, and the act of measuring that mass did not cause them to be something else. Right in hand with that is volume. And our last one here, viscosity, which is basically how thick a liquid is. So something like syrup is very viscous. Something like oil is really not viscous at all. But you can test that. You can measure their viscosities without changing what they are made of. It doesn't change their identity to measure these things. Physical changes go right in hand with that. They're changes that don't require you to break chemical bonds. Chemical bonds are not broken in the reactants, and this should say or. They are not broken in the reactants or formed in the products, because breaking those bonds would involve changing chemical identities, which we just don't. So you can talk about dry ice subliming. Remember, sublimation is from a solid straight to a gas. When this happens, it started as CO2, carbon dioxide, and it ended as CO2, carbon dioxide. We didn't break any bonds. We didn't change its identity. You can see the molecules here, 2 red atoms, 1 black atom. Here they've spread out. They have their own room now because they're a gas, but it's still 2 red atoms, 1 black atom. We didn't break them apart. So again, in a physical change, the identity of the material does not change. So this includes changes of state, like our dry ice subliming, or if you took some molten iron and you formed it into a broadsword or something and then let it solidify into the shape of that broadsword, that would just be a change of state. It's still iron, it's just a different phase now. Or changes in shape or form. So origami, right? You take some paper and you fold it into a different shape. It's still paper, you just folded it. It looks different, but it's still the same stuff. Or breaking a glass. You take a glass, you drop it on the floor, it breaks into a million pieces, but each of those pieces is still made of the same stuff as the original glass. You didn't change its identity, you just changed what it looks like. One last example here is dissolving sugar into water. You start with some sucrose, some table sugar, and it's solid, and then you dissolve it in water, and now it's something called aqueous. Aqueous means dissolved in water, but it's still sugar and water. Here we had just sugar molecules all packed together in crystals, and now those crystals have separated out into individual molecules, but they're still the same thing. It's still sugar. On the other side of that, we have our chemical properties and our chemical changes. And a chemical property is a characteristic that can only be observed or measured by subjecting it to a process that might change the identity of that substance. So examples of this would be reactivity. This is how much one substance reacts with another. Or pH, which has to do with how acidic something is. We're going to talk about acids and bases at the end of the year. There's ability to ferment. So if you've ever had something like kimchi or kombucha or even yogurt, you have experienced fermentation. Because yogurt starts its life as milk that is then mixed with bacteria, and it goes through this really long process. And when it's done, it is not milk anymore. Right? Milk and yogurt are two distinct things. So going through the process of fermentation, testing, can I ferment milk, changed it into something that's not milk anymore. Another example is ability to oxidize. And one type of oxidation is rusting. So you might take a piece of iron and you might think to yourself, I wonder if I can oxidize this piece of iron. I wonder if that's a chemical property that it has. The only way to know for sure is to stick it outside in the rain and let it hang out for a while and see if it rusts. But once it's done that, it is not iron anymore. You wouldn't want to use that for the same things you would use a piece of iron for, because you have changed it into rust now. It's not iron. You've changed its identity. Two other big ones are flammability, right? Will it burn? And toxicity. So flammability, again, the only way to test whether something is flammable is to set it on fire and see if it burns. But once it has burned, say we're talking about a piece of paper, right? The only way to find out if that paper is going to burn is to burn it. But once you've burned it, it's not paper anymore. By testing the property, you changed the identity. Same with toxicity. This is how likely a substance is to harm people or animals. The only way to know for sure whether something is going to be harmful is to see if it harms you. So if you've ever had a fire ant bite, which we all probably have because we live in Texas, you have experienced this. When that ant bites you, or actually it's a sting, when that ant stings you, it's injecting you with formic acid, which is harmful to your body. It's harmful to your cells. But as it is harming your cells are reacting with it and changing it into something else. So the process of that acid reacting with your cells and hurting you, being toxic to you, actually changes the acid into something else. So again, testing whether it hurts makes it into a different substance. Testing chemical properties changes the identity of the substance. Chemical changes, once again, go hand in hand with that. In a chemical change, chemical bonds are broken in the reactants and they are formed in the products, which means the atoms are rearranged. And if you are rearranging atoms in your substance, you are creating new materials. You're changing the identity. So there's an example of this right here. Theoretically, this should look kind of familiar. You should have learned it in biology. This is the process of photosynthesis, right? We're starting with some carbon dioxide, reacting with some water to produce glucose and oxygen. And as you can see, we start with these as our reactants and with these as our products. These are not the same materials we started and ended with. We broke bonds between this carbon and oxygen, between this hydrogen and oxygen. We broke these bonds, we rearranged these atoms, and we put them back together in a different configuration. So the identities changed. Pretty easy to tell when you've got a chemical change going on. Couple of good indicators. Those are an energy change. So this would be heat being released so that it feels hot. This would be heat being absorbed so that it feels cold. This would be production of light or heat. Sort of said that again. Anything that feels this way or looks this way, that's an energy change, and that is the sure sign of a chemical reaction. Another indicator is the production of a gas. And this one you have to be careful with, because this is not, I put water on the stove and boiled it and now it's a gas. This is a production of a gas without actively changing the temperature. This is, I put a piece of solid into some liquid and now it's a gas. That is not a normal thing. That is not something that happens physically. That must have been a chemical change. Similarly, a formation of a precipitate. And a precipitate is a solid. Once again, this is not, I filled my ice tray with water and put it in the freezer and now it's solid. This is, I took a liquid and I mixed it with another liquid and now it's a solid. This is something you would not expect to happen. It's an unexpected solid, just like this is an unexpected gas. Another good example is the formation of an odor. If you mix two things together and now they smell, that's a chemical change. If you leave milk in your fridge for just a little too long and you pull it out and now it doesn't really smell like milk anymore, that's the formation of an odor. That's a chemical change. There's no going back to the milk you had before. It has changed its identity. It's changed at a chemical level. And our last example is a color change. And again, this is an unexpected color change. So that milk you left in your fridge, maybe you left it there for a really long time and you pulled it out and it was white when it went into the fridge and now it's a little bit yellow. That's an unexpected color change. You did not put yellow dye in that milk. It kind of got there on its own. It might even have formed a spontaneous solid if you left it there way, way too long. It went in smelling like milk and it was white and it was a liquid and it came out smelling like death and it's yellow and it's solid. That is 3 signs that you just went through a chemical change. All right, the last thing we need to talk about here are intensive and extensive properties. So your intensive properties don't depend on the amount of matter that is present. Your intensive, those are independent. Independent meaning strong independent property, it don't need no substance. These would be things like color, odor, density, melting point, malleability, which again is like moldability, boiling point, ductility, which is drawing out into thin wires, conductivity, how well it conducts electricity or heat, luster, how shiny it is, or temperature. These are things that are not going to change if you change the amount of stuff that you have. If I had a cup of water that's just been sitting out for, I don't know, a day, it's going to be the temperature of the room. It's going to be about 25 degrees Celsius. If I pour half of that water out and then measure my new water level, which would be down here somewhere, the temperature won't have changed just because I changed how much stuff was there. If it was 25 degrees when it was a full glass of water, it's 25 degrees when it's a half a glass of water. Because these properties, these intensive properties, they don't care how much stuff you have. If it is a teaspoon of water, it's going to have a density of 1. And if it is a huge industrial tank filled with water, that huge industrial tank of water is going to have a density of 1. Play-Doh is malleable. It doesn't matter if you have the world's biggest wad of Play-Doh and it doesn't matter if it's just a little bit of Play-Doh stuck under your fingernails. Until you let it dry out and change, it is malleable. So these are all properties that don't depend on the amount of stuff that you have. The opposite of this would be extensive properties, which do depend on the amount of stuff that you have. These are pretty more straightforward. We have not that many examples of extensive properties, and most of them are intensive. So mass obviously depends on how much stuff you have. If I have a handful of pennies and I weigh my pennies, they're going to have a certain mass. And then if I take just one penny and I put it on the scale, it's obviously not going to weigh as much because it's not as much stuff. If I had my glass of water from earlier, When it was a full glass of water, it had a certain volume. And then I took away some of the water and now it has less volume. Or length and width. If I have a sheet of paper that's 8.5 by 11 inches and then I tear that paper in half, throw half of it away, the other half is going to have less length to it because I got rid of some of the paper. So pretty much when it's an extensive property, it's pretty clear that it's extensive because it's kind of just, yes, of course, there's less stuff, so there's less stuff. The rest of them tend to be intensive, so just, I don't know, keep that in mind. At this point, you've got some time to do some practice in your book. You have 3 problems that'll ask you to identify whether something is a physical or a chemical change and explain why. And then you've got just a lot of properties, and you're going to decide if they're physical or chemical, and you're going to decide if they're intensive or extensive. So take a minute, work through this, and when you're ready to check your answers, go ahead and unpause the video. All right, so this is what you should have gotten. Your changes should have been chemical and then physical, and your properties should have looked like this. They were all intensive properties, because again, your extensive properties are really easy to pick out of a list. They are things you can physically measure. So if this is not what you got for your answers, hopefully you understand why, or you can go check the key on my site to get a more thorough explanation for those first 3 problems. And if you did get these all right and you're feeling good, it means you're ready to work on Quest. So go ahead and move over there, get your assignment done. This is it. This is all you get to learn for Unit 1. From this point on, it is review and study and get ready for your test. So don't forget to go back over the stuff that we did beginning of school, accuracy, precision, percent error. Study your polyatomic ions. They are fair game on your test. Make sure you are looking at all of the stuff, not just the recent stuff. Work on your lab if you're not done with that. And as always, if you are uncomfortable with something, want some clarification or just more explanation, of course, always feel free to come see me or some other teacher. So good luck and happy studying.